Good morning, everyone. Hope you can see my screen and you can hear me. So I believe you have got the um, assignment one. I have shared the assignment one. So if you have not got, mail me, then I can forward it to you. So please follow the instructions for the submission of the assignment one as given in the email. Please follow, put the uh, assignment in the given Google form only. Otherwise, it will be tough to track your assignments later. So it is better if you can put the assignments on the Google form. It will be easy to find out actually and give markings and all. Right. So that is a thing. So I have given the assignment till the regression analysis. So we'll consider the probability and the part what we had done in for the next assignment. So please follow the time limit, whatever date is given to you. Please follow that and submit within that particular date because once again, since already you had done uh, so like after 19th September, 19th September, I would suggest I'll give the next assignment. So that it will continue anyway, right? So yeah, last class we had talked about the probability basics of the probability. We have described like it is a non and now the given situation is that it cannot be a deterministic process. So the system can be non-deterministic, specifically like till the regression models and regression lines. Whatever till now we have discussed. If it is like a specific single model which gives you straight line equation or this kind of equations which gives you definite estimate numbers in terms of some models, some equations where there is no non-definitive situation is there. But it is possible that in this particular part, the same in the scenario, the possibility of the non-definitiveness may come, the probability situation may come as you might have worked on the machine learning and all this kind of situations you have seen where probabilities happen that we defined some set of features, right? If we define some set of features, on those features we define in the terms of some random variables under some random experiment. So we start with something called random experiment, right? So as we have started in the probability also, but here also some random experiment may happen. Suppose as if I want to find out in a set of a garage, there are a lot of different type of cars, different type of vehicles are there. So of course, two wheelers, three wheelers, four wheelers, and all these things could be there. And so we can find out or we can cluster this particular vehicles in terms of the how many wheelers are there. Probably that is could be the say function one or the feature one. If two, the feature two could be the what is the color of that particular cases. Then it might be a different set of clusters, and like this we can define n number of features, and this n number of features will give you a set of probability in terms of how many total numbers of vehicles and in the in the other on the top there will be the favorable cases, right? So this kind of cases, of course, the features can get the weightage in terms of the probability. So for this kind of situations where there is a probabilistic situations where you got a multiple set of features and you got the respective frequencies, how to deal with those and what kind of models are possible and what kind of parametric calculations are possible, that we will see today, and we'll try to understand how the basis of the random variables comes into the picture. Of course, all random variables comes under the some random experiment. A random experiment can be anything. Like you're tossing a coin, you can toss two coins. You throw a dice, say you throw a six dice. Any things under the sun, we can define as a kind of a random experiment. Under the random experiment, so basically RE under the random experiment, we generally define some set of random variable. Now, say suppose I am tossing two coins together. That is a random experiment, and on that particular note, that if I define the number of getting two heads, if I define like that way, that is basically the random variable. A number of getting heads, simply, that would be the random variable. So that's how under one random experiment, we can define a multiple types of random variables. Now these random variables again can be two types. One is discrete random variable, and one is called continuous random variable, right? So say random variable I'm defining as x. So that could be a discrete random variable, that could be a continuous random variable. Of course, from the name you can understand some experiments will create some definite set of data, right? So like suppose if you are throwing a dice, you will get 1, 2, 3, 4, 5, 6. That's it. Like it is not 1.1 or it can be 2.9. It cannot be like those numbers. There are definite specific numbers will be there. Discrete numbers will be there. But some cases or probably the maximum cases, we have some set of random variables, which random variables will give you certain kind of a innumerable kind of a number. Suppose distribution of a height in a particular class. Say the salary structure of a whole country. Probably something this kind of situations. You see, it is not a specific some set of discrete number. It can be any kind of a number. So for this kind of cases, of course, these are the continuous variables. So let's define the discrete and continuous variable in a typical statistical fashion. So for the discrete random variable, short form we generally are write as a DRV. So here we are discrete random variable. So a random variable which assumes a finite number of a number or countably infinite values is called the discrete random variable. Right? So basically, this is a kind of a similar term. So basically, it is either it is get a finite number or it is called a countable infinite number. Similar same things, but in a notation wise in a statistical sense, so it's generally defined like this way. If the numbers basically it is getting the this kind of a numbers, then it is basically discrete random variable, and if the number is uncountably infinite number of values, then it is continuous random variable. So this is the definitions. So typically, this is a discrete random variable. This is a continuous random variable. Of course, in simple sense, you can think of like discrete random variable. We take a certain set of numbers, discrete numbers, and continuous variable. Typically, it will be an equation. On the basis of the equations, we have to deal with the numbers. So now, if the x, if I write a capital numbers, that is basically the random variable. So random variable can take the values, say x1, x2. So like if in terms of any variables, if I can take this x value with the probability, say p1, p2, p, right? So this probability, sorry, this random variable along with this probability, this is basically defined as a probability distribution function for this distribution for the x. So basically, if I have a x that is a random variable with a in numbers, in set of numbers, and along with that, I can find out the respective probabilities by two process. Either it will, if it is a discrete process, then it will be a kind of a this x1 is equal to this number, some kind of numbers it will get, some discrete number it will be there. Otherwise, there will be one equation where if you put this x1, x2, x3, and you will get some probabilistic value. So anyway, this particular set basically is called the this probability distribution function. I would simply probability distribution. Right? Now, if this probability distribution is there, now for either discrete or the continuous set, we define this fx as the probability random variable x. If the capital letters, that means there is a this random that is a random variable. So p of x is equal to small x. So basically, it can take any value as a small x, which is defined as function fx. Now, for discrete and the continuous case, two system will be different. So let me just make this RV. Now for the discrete random variable, it is called the probability distribution is called PMF. That is called probability mass function. And probability distribution here in the continuous is called the PDF. So probability density function. So this is a probability mass function, and this is the probability density function. Now for each case here, if I take as a if x basically p, as we write x is equal to x is defined as the function of fx for both the cases, but it will always follow two things. This fx, these are nothing but the probability. Fx is nothing but the probability. Okay, so it follows two parameters, two properties. One is fx greater than is equal to 0. Again, both are same. Greater than is equal to 0. Of course, probability cannot be less than, negative probability cannot be there. So it should be more than 0. And second thing is that for this case, summation fx I want to n, given that there are n number of observations are there, then it would be is equal to 1, summation of all this. And the corresponding similar property for the continuous case would be minus infinity to plus infinity integration of fx dx would be 1. So any probability distribution, be it discrete, be it continuous, it always follows these two sets. Each and every probability has to be greater than is equal to 0, and summation for the discrete case, summation I want to n, all the basically all the distribution numbers should be is equal to 1. So all the summation of all the probabilities should be 1, and the same things corresponding to the continuous variables, it will be the integration of minus infinity to plus. So basically the whole range basically. Of course, depending on the function, the range can be different. The function may not be defined on the whole minus infinity to plus infinity region. So we need to focus on that particular region also, which is on the basis of the region basically. If you integrate the whole the function, the area under the particular curve would be summation of the whole curve should be is equal to 1. So these two properties always PDF and the PMF has to follow. Now, if we take the things case by case, let's start with the discrete random variable. It is a bit easy to understand. Let's start with the PMF. Let's see how the PMF would look like. A random experiment as in mutually exclusive and exhaustive. Anyway, it has to be exhaustive uh, outcome. Then the PMF can be written as the PI. So I can write this x is equal to xi. So I could have write this x is equal to xi. Like this. So x1 can take probability value p1, x2 can take probability value p2, so on. Since I got in numbers, so it can get probability value again. So this is the PMF, probability mass function for a discrete random variable. So if this PMF is there, as we have told that all the PI has to be greater than is equal to 0. That is the first condition for being a PMF. And the second condition would be summation of I1 to n PI would be 1. So basically P1, P2, P3, if you add till Pn, that should give you the value 1. If it is not anything less than 1 or it is not anything more than 1, it should be exactly 1. Okay. Now, of course, if this is the definitions, then what are the statistical parameters we can calculate from this particular thing? Of course, I'll show you one practical example on the basic on two practical examples. So from there, basically, we'll see the application of the discrete random variables. So first is obviously something. If we have this kind of a PMF, we can calculate mean from this. So previously we started with the mean average. So here this particular mean is basically is called the expectation. So expectation typically shown by E of x. This is nothing but the mean in terms of probabilistic situation, or we also call it as a gain. Only gain or the expected gain. This kind of words basically can be used. Basically, if you find out this kind of word, that is the meaning is that you are supposed to calculate the mean. So how should I find out this mean? So E of x is P1 x1, P2 x2 till the P of Pn xn. So basically the multiplication of the respective probability as well as the respective random variable number values. So that is basically, that's how basically we find out the mean. Right? So this where of course always some assumption of pi has to be 1, that is always there. So we find out the expectations or the mean of this particular random variables using this equation for any discrete situation. And of course, if we are calculating the mean, the variance would be there obviously. So the variance does not have any special name. So this variance sigma x squared, that is the variance of x, is defined as expectation of x minus ex whole square. Right? So this is kind of a operator, you can say. So x minus ex whole square. This is the uh, first. If you remember the our first classes, we had talked about like the two equations for variance always. So this is the kind of the initial equation. So from there, we generally do some calculations and do some simplifications, and we create our own calculating type equations. This is the initial equation. So basically, the same concept is same itself. From each and every random variable values, we are basically minusing, doing the minus of the. We're trying to find out the distance between these two values, e and its mean values, and we are doing the square. That's it. That is a normal thing we are doing. The same concepts it was there in the your standard scenario. So let's little bit some simplify this. So basically, it is nothing but a minus b whole square. So I'll just expand the a minus b x square minus 2x of ex to a b plus b square, right? So now let's put this operator e everywhere. So first, if you get the variable straightforward, of course, it will take the expectation operator e of x square, and in this particular second operations e of x is always already a constant value, 2 is already constant value, so it does not affect by the parameter e. Now if I so only variable
नहीं
in this
अरे मतलब सामान जो ये करने वाला था ना घर में जो अच्छा अच्छा टाइम तो लगेगा सही है सही है
so the x is the only variable here, so already it will be e of x multiplied by e of x, and since e of x as a square value, there is nothing to do with that because it is already constant. It is already constant value, so expectation on the constant value does not affect. So it will be still be the same as a e of x square values. So if you simplify this, it will find out as a minus 2 of e of x whole square plus e of x whole square. So eventually it will become a e of x square minus e of x whole square. So this is the working formula for expectation based variance. But of course, you know the formula of the e of x. Of course, you can from there you can find out the e of x whole square. But what is the value of this e x square? How should I find out this? We should focus on this. So e of x square is nothing but summation I was doing pi into xi square. That is the e of x square. So that's how we can find out the e of x square. So basically, we know e of x square and e of x. So then we can find out the variance. We'll see the example, of course. We'll find out. So two important formula you can keep this. Probably later we can use these things. That if x and y two are two independent variables, random variables, then e of x plus y would be e of x plus e of y. Both are variables anyway. And e of x multiplied by 5 would be e of x multiplied by e of. So these are two formula. Probably we'll use some point of time later. Okay. So more or less, these are the formula. One more thing is there, something is CTF is there, but we will talk about that later. Let's first see first two formula. Sorry, two examples on this. First one is a kind of a the for because of what we started the learning statistics or the probability, that is the basically the gambling. So the first problem is on the gambling. So very basic kind of gambling. A man tosses a coin twice and is received rupees 2 if a head is shown and loses rupee 1 if a tail comes. Right. So very basic gambling kind of a problem. So we are telling that okay, man tosses a coin twice. So it can be, of course, in numbers, in times, and in numbers. So, but the thing is that we're tossing two times. In this particular two times toss, if you get a head, you'll win a 2 rupees. But if you get a tail, you are going to lose. You have to give 1 rupee back. So, if this is a kind of a game, to then find the expected gain and the variance. Right. So, typical statistical game based problem. So let's first, for this kind of a problem, we need to create a table. On the basis of that, we need to define basically what is the probability value and what is the x value, that is the gain value. So first thing is that we need to find out what are the outcome, then the probability, then the gain, that is the actual random variables. Then of course, for our calculation purpose, I need to find out the pi into xi and pi into xi square for the variance part. First, let's understand what are the possible outcomes we have. We are tossing the coin twice, right? So twice, if you're tossing the coin, so of course we got three options can be done. Either we can get two heads, or we can get say one head, one tail. Of course, it could be HT or TH, either cases, but the gain for the both cases would be same, HT or TH. Sequence wise, it will be different, but anyway, final outcome would be same. And it would be two tails. Correct. Now, of course, if I get two heads, either way, as we have discussed, like how we should find out the probability. That's why I see the application of the probability is coming here. So first problem, I guess, on the coin problem we had done, either option way we can do, either we can find out like if I toss two coins, I'll get four possible options: H, 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 T, T, H, and T, T. So getting two heads, of course, the probability will be 1/4. Or other way, you can say that okay, getting one head, the probability is half, and another getting a head is half. Since both are independent events, I can say half multiplied by half. That is 1/4. Either way is same. One head, one tail. It would be HT and TH. So 2/4 or two times half multiplication. So it will become a half, right? And two tails, of course, TT out of four. So it would be 1/4. Of course, always whenever you are writing or you think that okay, your probability part are done. So always check this summation of this value has to be 1. Otherwise, as I told, it won't be a PMF. Correct? So this is the probability. So 1/4, half, and 1/4. So now let's find out the x values. So if I get two heads, that means that first head I'll get gain 2 rupees. Second head I'll get 2 rupees. So finally I'll get 4 rupees. Correct. One head, one tail. So either it will get, if say it is HT, that means for one head I'll get plus 2 rupees. For one tail, I'll get minus 1 rupee. That is eventually is 1. So either it will be 2 plus minus 1, or it will be minus 1 plus 2. Either cases, it will be at the end of the day, it will be gain of 1 rupee. Next, two tails. So both the cases, so minus 1 plus minus 1. So it will be minus 2. For the two tails, my gain is minus 2. So if I just want to write the PMF table, the PMF table would be look something like this: 4, 1, minus 2, 1 by 4, half, 1 by 4. This particular table is the PMF table for this particular problem. Okay, probability mass function for this particular random variable x, which is defined by this game, is given by this probability distribution function. It is not density function, okay? This is distribution function. So we can be confused in it. Of course, I need to find out the final expected gain on the all over this particular game, and I need to find out the variance. Of course, we remember the formula is the p into x, pi into xi for the expected gain. So straightforward, I got the gain in this column, I got the probability in this particular column. Let's multiply. So this would be 1, this would be half, this would be minus half, right? So if I add these, it will be 1, right? So basically, the expectation of x, the gain would be 1 rupee, positive 1 rupee at least. Okay? Expected final gain. Basically, that means that if you play this particular game for a long time, your final chance would be to gain 1 rupee. So there is a gain situation is there in this particular game. Of course, you can play this game. But what is the variance? Let's find out the variance. Basically, of course, as you know that the less the variance, the better for you. The more the variance, of course, it will be like kind of a bigger surfaced kind of a card. So it is having a big standard deviation is not that good. But how should I calculate? Of course, I need to first do the square of this particular column. Again, is x square. So 4, 16 into 1 by 4, that is 4. 1 square 1, so it's half. Minus 2 become plus 4 multiplied by 1 by 4, and that become 1. Now if I add this 5, 5 and a half, that means 11 by 2. Now this is nothing but ex square. Ex square is this value. I want to, in this case, 3 pi into xi square. So that has become 11 by 2, but this is not the variance. Variance is e of x square minus e of x whole square, right? So 11 by 2 minus 1 square, 11 by 2 minus 1, that is 9 by 2, that is 4.5. So basically, minus 4.5 to 5 plus 4.5, anything you can win in these situations with the mean of 1. So that's how basically the application of mean and standard deviation we can use for gambling purposes. Should not do, but this is the practical example, practical application of probability or the game in this area. Next, another kind of a business practical related problem, that is a man has a choice of having either hot snacks, short form is this, better I use this, or ice cream stall. So you got two options, either hot snacks or ice cream stall. If it is cool summer, he should make rupees 5,000 by running for snacks stall. But if hot summer, then he only can expect rupees 1,000. So basically, if the summer is cool summer, then you can make rupees 5,000 by selling the um, hot snacks stall. But the summer is hot, of course, practical scenario. If the summer is hot, of course, nobody is going to buy hot snacks. So for that case, he is going to expect rupees 1,000 sales, right? On the other hand, if it is cool summer, but it is a hot summer, ice cream gives profit of, let's say, keep the sales of rupees 6,500, but rupees 1,000 if it is full summer. So if it is hot summer, rupees 6,500 for the ice cream. But if it is a hot school summer, then rupees 1,000 for the ice cream. Now, there is a 40% chance of summer being hot. So, should you opt for hot snacks or ice cream stall? Practical example, right? So, again, like for the you got two options: hot snacks or the ice cream, both stall. If it is a cool summer, then people of course will eat the hot snacks, will make 5,000. And if the it is a hot summer, then the hot snacks will give you rupees 1,000. On the other hand, if it is a hot summer, ice cream stall will give you rupees 6,500. But if it is a cool summer, it will give you the rupees 1,000. Now there is a 40% chance that it will be a hot summer. Then of course 60% chance it is a cool summer. So then which particular stall person should go? So for this case also, of course, variance is not required, but the mean is going to help me. Expected gain is going to help me. So you can create a table like this. So if the summer is hot or cool, for hot summer, chance is 40%, that is probability is 4. Cool summer, of course, it should be 0.6. Now gain for hot snacks and here gain for ice cream, right? So for the hot summer hot snacks, gain is 1,000 rupees. and gain for ice cream is 6,500 rupees. For cool summer, gain is 5,000 rupees. Here it is 1,000 rupees. Now let's find out, because this is the P, this is the X for hot snacks, this is X for ice cream. Right? So let's find out the expected gain from, say, first is go, let's go for the hot snacks. Take this. So summation Pi into say two cases are there. So typically zero point 0.4 with 1,000 and zero point 0.6 with the 5,000. If we calculate this, should be come as 400 plus 3,000, 3,400. Right? So this is the number. Now expected gain from asking. So it's asking into same formula, same process. So here it will be zero point 0.4 into 1,000 and zero point 0.6 into zero point 0.4 into 6,500. I'm looking for this column, and zero point 0.6 into 1,000. Right? 4 into 6,500 and zero point 0.6 into 1,000. This is, I think, 2,600. This is 600. So 3,200. That means here 3,400, here 3,200. That means the person should go for hot snacks. So that's the kind of a practical example we can think of in this part. Now, one more concept, if you remember, we had also done this in our general classes. That is, something is called as a cumulative frequency. Right? Cumulative frequency. We try to find out kind of a increasing kind of a graph. Of course, since the frequency is non-negative numbers, if we keep on adding the frequencies, of course, one will get a non-negative, ever increasing one kind of a graph. So same concepts we generally keep putting here. There is something is called the CDF. That is the cumulative distribution function. For both the cases, cumulative distribution function may happen. So for the discrete also, continuous also. So if I define this, first I'll try to finish the discrete random variable along with PMAF, its CDF, everything. Then I'll jump into the continuous. A lot of the integrations and everything is there. So I'll just keep the things here. So that's why I'm defining it here. So I'll do the CDF of continuous variable also later. So definition wise, the probability that random variable x takes value is then or equal to a specified value, right? So basically, till the particular value x, same concept, till the particular value of x, how much probability do you have, right? So that is the basically the concept. So typically here, CDF is defined, that if you remember, the CDF is defined by the capital F of x. Remember, the PMF and the PDF always defined in a short format. There is a small fx. CDF is shown as a capital Fx. So fx, if I try to define this, this is nothing but this. Again, if I write fx, that is p x is equal to x. Okay? This is a basic difference between these two. So basically, it is keep on adding, nothing but it is keep on adding, and this is on that particular number. What is the value? Right? So, and probably fx will be as a limit. So of course, maximum fx would be one. So you could keep on adding the probabilities at the same point. Some point of time it will be one, right? So that is the value. Now for a discrete case, if I want to write a CDF for a PMF, first let me write down the this is the PMF for a discrete random variable with the probability p. So then the fx can be written as p1 when x is less than equal to x1, p1 plus p2 and x is less than x2. Of course, it is expected that it is the x1 is less than x2 and it is in increasing mode like that. Yeah, not increasing mode anymore, but it is the next number. So p1 plus p2 plus p3 is then x3 till this all the numbers, right? Now say if I want to find out in between, say x between x 3 and x7. Just I'm giving an example. That means that p x less than x7 minus p x less than x3. Small. So like this we can find out in this particular. Now let's see how the what is the practical implications of this. Say an unbiased one is shown three times. If the random variable x denotes a number of heads, so x denotes the number of heads basically, then find the CDF of x. Right? So how can I find out the CDF of x? Typically, CDF actually are more tactical in the continuous section, not the discrete scenario. Because in discrete scenario, already you know the on the to the point scenario based number. So basically, if I want to find out what is the value in between these, I can just find out in terms of the total numbers, and you can expect to get the numbers. But anyway, if you want to find out, see in between these, like this kind of a scenario, of course, we have to find out the CTF. But anyway, let's see. So suppose here, so basically you're throwing a coin three times, and your random variable is x. So x denotes the number of heads you are getting. So number of, if you are um, um, getting the number of heads for three tosses, so what are the possible options? That could be 0, 1, 2, and 3. Four options would be there. Now the probability, let's write the probability here. So it is 0 hits. That means that all the tail, four tails are there. So three tails are there. Of course, the probability will be 1 by 8. One head, two tails are there. So basically, this is the number of one head. That means two tails are there. So three options could be there: head, tail, head. Sorry, head, tail, 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 head, tail, and tail, 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 head. Right. So that would be 3 by 8. Two heads are there. That means that head, tail, head, and tail, head. Right. Again, 3 by 8. And three heads are there. Only one option, head. So again, 1 by 8. Again, observe, since it is a PMF, the addition of the all the summation of the fx should be 1, and of course none of the fx should be less than or equal less than 0. It can be equal to 0, but it cannot be less. Okay. So basically it's a PF. Now let's create this CTF. So f of 0 means that p is less than equal to 0. That means p x is 0. That means 1 by 8. Correct. F of 1, that means px less than equal to 1. That means px is 0 plus px is 1. So we got 1 by 8 plus 3 by 8. So 4 by 8 eventually is half. Third, f of 2 here, px less than 2. That means px is 0 plus px is 1 plus px is 2. So 1 by 8 plus 3 by 8 plus 3 by 8. So, so 7 by 8. Right. And the final one, if 3 px then equal to 3. So x is equal to 0, 1, 2, and 3. Right. So all the numbers will come eventually. 1 by 8 plus 3 by 8 plus 3 by 8 plus 1 by 8. So 1. As I told, it should be between 0 and 1. So which is there. So eventually that is the CDF of a discrete random variable. So if this is a numbers are quite high, of course you can find out, say in between 2 and 3 how much probability is there. So that does not have meaning for this particular case, but that's how basically you can find out, even that if the number is quite, say, 12 or say 100 discrete variables are there, then the CDF would be useful if you try to find out the interval based in kind of probability situation. So this is all about the discrete additions and discrete random variable. But as you know, in our real life, of course, the number of random variable, random experiments, whatever we do, those yields random, continuous kind of a output, continuous random variables. So let's focus on the random, continuous random variables. First thing, of course, the PDF. There it was PMF. Now it is PDF. Now probability density function. So probability density function typically would be some kind of equation. It is not a single number. Just it would be some number. So we have to deal with in terms of equations here. Equations or the kind of um, random variables in terms of the normal equations. Let's see. Let's see. So of course, as I told, as in a PDF, it has to be the function has to be greater than is equal to zero. Condition number one. Condition number two would be integration minus infinity to plus infinity fx dx has to be one because it is a probability. At the end of the day, it is a probability. Right? First kind of examples. Let's start with that. That is given that any kind of equation. First, we should see that okay, this particular equation can be a PDF or not. So suppose like uh, example one can be very basic one, that is the following PDF or not? Yeah. So how it is given? So say if it's looks something like this, 2x which is in between 0 to 1, 4 minus 2x between 1, sorry, 1 to 2 and 0 otherwise. Right? Suppose this is a kind of a uh, defined function set is given. So first we need to find out that it is PDF. So we'll start with of course with the first um, property. First thing, if you just observe this case, that is first option is 2x. 2x is in between 0 to 1. So if I put any numbers here, so it will be more than 0. At least if I put the 0 also, it would be 0, right? And otherwise it is obviously 0. It is not some minus 5, minus 10, something, some number is coming. If it is there, some say suppose it is instead of having 0, there is a it's written as a minus 10. So instantly you can tell that okay, this is not a PDF because that cannot take any value less than 0 as we have defined here. What about this particular interval? In this particular interval, the maximum value it can take is 2. So that means if I put this value 2 here, so it will be 0 again. Still, since it is not cannot be negative till now, as if again the same thing like if it is not 1 to 2, it is suppose it is 1 to 3, then it would be like if I may put maximum 3, it would be 6, then it would be minus 2. Then it is possible that it is not a, not possible, it is obviously not a PDF. So like this, we can check this uh, option one, correct? So that is the one, option one is has been checked and passed. So now we need to find out about the option two. That summation integration of minus infinity to infinity fx dx. If this number is giving me one or not, if it does not give me one, that means it is not a PDF. If it is gives one, then it is a PDF. Of course, you can see it is given a full area integration, but our system does not go till that part. So basically, what we can divide this minus infinity to 0 fx dx 0 to 1 fx dx because it has a different values, right? 1 to 2 fx dx and finally 2 to infinity fx dx. Now, as is told that except these two intervals, it is 0 otherwise. That means that I can say that this number is 0 and this number is 0. So, no need to do this integration. I have to do only two sets of integration, that 0 to 1 and 1 to 2. So, let's go with the 0 to 1. So, 0 to 1 is 2x dx, and 1 to 2 that is 4 minus 2x dx. Correct? Let's do this integration. So remember, this is x squared by 2 with limit of 0 to 1 plus 4 is the integration is 4x minus 2x squared by 2 to 1. So 4 minus x squared with a limit of 1 to 2. This would be again 1. So 1 minus 0 is 1. Here it is 8 minus 4, that is 4. 1, 4 minus 1, that is 3. So it has become 1 plus 1, that is 2. That means this is not a PDF. It exactly has to be 1. If it is not, then it is not a PDF. Right? Let's take. This is a PDF. Of course, we'll do it more problems, but let's define the CDF also in this particular case. The CDF of continuous random variable would be given as, so if it's minus infinity to x fx dx. CDF will be given like this, or if it is within, then we can write like this way. C, sorry, D, that means C2D fx dx, which also can be written as if D minus f of C. So we can write, so basically what we are doing, so basically we are basically telling that if D is nothing but the Px, sorry, Px less than D, that is minus infinity to T fx dx, right? That means that opposite way, if I just want to write, fx is basically nothing but the derivative of the function fx, right? So this, so you can basically remember this. So as if there is a reference line in the minus infinity. So from the minus infinity to that particular value x, if you find out the area under that particular curve, that is going to give you the CDF. Anyway, the CDF has a very more application in the continuous variable. Of course, basically, if you typically find out a PDF and if you ask it for a continuous variable, say as if the marks, right? So it works with marks, and we generally create a bell shape or the normalized distribution for the numbers on the basis of the mean and the standard deviation and all these things we do, right? So for this particular case, if somebody asks you what is the probability that a student got a 550 marks or 60 marks, that does not as such mean anything. If it is not a discrete particular kind of situations, because it can take any kind of a number. Practically, if it's the your sample is quite huge, you can get a any possible kind of a number, right? So given that, of course, your marking policy. So let's take it as a kind of ideal way that it can take actually any kind of number. So that is a case. So, but if you may ask, okay, less than 50, how many people are there? Or in between 50 to 70, how many people are there? those are quite a meaningful questions, right? So that's why the CDF has a more application. We'll see talk about more this during the actual normal distribution scenario. That this is CDF has a more applications in this continuous variable area. Right? So let's now club this PDF and the CDF, and let's try to find out what kind of problem we can explain here. So a company what is the demand production using the following PDF. It is given by x is k into x minus 1, 2 minus x, where x is between 1 and 2. K value we do not know, some constant value. So of course, for this kind of a scenario, if it is given that it is a certified PDF, then you have to assume that it is a PDF. So for this case, find out A and find out the CDF. Third, find probability that x less than 5 by 4 and probability x greater than 3 by 2 and find probability x lies between 5 by 4 and 3 by 2. So basically, we'll understand every possible aspect from this particular problem. So, of course, we got the PDF here. First thing, of course, I need to find out the unknown value k here. So, we'll go for the second property. Of course, we cannot find out the first property for the time being because we have no idea about the k value. But always we know that it is definite that if we take it from minus infinity to plus infinity, that should be 1. So this part already we know, and we are going to use this particular property. Typically, we are going to integrate this equation e x minus 1, 2 minus x dx. This has to be 1. But of course, it is not minus infinity to plus infinity because we have defined this as a minus 1 to plus 1. So it is not required to put minus infinity to plus infinity. I'll just replace minus infinity and plus infinity here by 1 to 2. Right? It's multiplied 3x minus x square minus 2. So let's do the integration. Key has nothing to do with this. Integration 3x would be 3x square by 2. So bx cubed by 3 should be 2x with a limit of 1 to 2. Let's put the numbers. So it is to put 2, it will be 6 minus 8 by 3 minus 4 minus 3 by 2 minus 1 by 3 minus 2 to 1. So eventually, if we simplify this, get k by 6 is equal to 1. So k should be 6. So that's how you can find out the unknown parameter, unknown constant. In general, we keep as an unknown constant kind of problems you'll find a lot. So we got this. So basically, we got the function fx as 6 into 3x minus 2. Right? So where x is between 1 and 2. Now, next problem is to find out the uh, CDF. That is the second. So capital X. First formula minus fx dx fx dx. So please observe this is minus infinity to x. Okay. So the formula, whatever output of this particular integration will come, it should come in terms of a variable. It should put some value, right? A, B, C, D, 1 to 10, 5, 15, something, some numbers I should put. So it is not the same integration, minus infinity to plus infinity. It is not that. It is minus infinity to x. X is a some unknown. But reason, of course, it is in between 1 to 2. That means that we put focus on the lower boundary because it is as if, let's say, the graph something like this. So till this particular x value I am doing from minus infinity, but minus infinity to 1, somewhere 1 is there. There is no value is there, it is 0. So we are not going to take care of that part. Only from 1 to x we are going to integrate. So let's integrate from 1 to that particular number. So now my new integration would be so this input is equal to 1, right? It is not that. This is a trying to find out the CDF. So let's do the integration. 3x squared by 2, x cubed by 3, 2x, 1, 2. So let's put this x, always it will be same itself. So same. If you want to change the variable, it is up to you. Do the variable change. So typically one more constant scenario will come into the picture. 2 minus 1 by 3 and minus 2. So this is if you put the 1 up, you get. You can simplify this. Okay, in the simplified version, it will become 6, 6. 5 minus 12x plus 9x squared minus 2x cubed. Okay. So if you simplify this, we will eventually get this. So this is the CDF, capital FX on this. While finding out the CDF, anytime, suppose, say, for next question, it's given as px less than, say, 3 by 2. Typically, I should do the integration like minus infinity to 3 by 2 fx dx like this, which will become a1 to 3 by 2 fx dx, something like this. So every time you have to do integration if you just play with the PDF. So not to do this particular integration again and again, we have already integrated this particular part. So till this particular part already we know this particular graph as this equation. And I just keep on putting this value and I can find out quite easily. That is basically the good application of the CD. So anything less than or less than equal to, if you find out, just put the value. That's it. So simply 5 minus 12, 3 by 2 plus 9, 3 by 2 whole square, 2, 3 by 2 cube. Simply you just put the value, your value you are getting, that is the your less than. What if it is greater than? Suppose it is given as a greater than, sorry, greater than 5 by 4 was there, right? Let's say we will need to find out the greater than 3 by 2. So as per the problem, was x greater than 3 by 2. That means that 1 minus p is less than 3 by 2, which is this basically. So that means 1 minus f 3 by 2. So 1 minus half is half. So just remember, so for any graph, reference line is minus infinity to that particular number. Whatever area under this particular curve is there, that is the fx. Capital X. Okay. Second problem was number 3 was probability that x less than 5 by 4. It is straightforward. So if 5 by 4, put the values, job is done. Simplify something 5 by 3 2 will be. And the last one, probability that x lies between 5 by 4 and 3 by 2. Right? So that means this, that means if 5 by 4 minus, sorry, 2, which is bigger. I think 3 by 2 is bigger. So 3 by 2 minus 5. So, so it will be half minus 5 by 32, that is 11 by 30. So basically, we are reducing the time for the integration. So like already we have using some variable, we have defined the already integrated part. So this time we are just keep on putting these numbers and calculating the area under the curve, and which is basically nothing but the giving you the probability measurements. Let's see one more problem. Length of time in minute that a customer queues in a post office is a random variable and available key is a capital Q with PDF make it small t. If t is equal to C of A21 minus t square for t between 0 to 9. Clearly, t has observed till the 9 minute, 0 to 9 minute. So, on the basis of this 9 minute observations, the person has provided this model. Of course, C can be constant depending on it may be like depending on which particular post office you are going on the basis of that is particular constant rates change. It is me zero otherwise. Of course, the first problem would be just put this C is constant. Suppose first is and C, second is like the CDF, third is the and the probability that a customer will queue for more than 3 minutes. And the fourth is find the probability customer who is queuing for 3 minutes is also queuing for 7 minutes. Okay. These are four problems. So again, let's start with the first one, very basic one. That is the small fx is given as C81 minus t square, where between t is this. How should I find out the C? Always minus infinity plus infinity if x dx is equal to 1. In this case, since x is t, so let's integrate 0 to 9 c to 1 minus t square dt is equal to 1. To the next two five parts. So 0 to 9 c h1 t dt minus x to the comma 0 to 9 t square dt. So it will become 81, not t, right? There should only be t. Only 81. 81 dt. It will be dt only the integration So it will be t. So 9 t square t cube by 3, that is 9 1. So here it will become a 3 2 1 multiplied 9. Here it will become 9 cube by 3. It is minus 0. So forget about that part. So 81 is 9 square. So that means that it is 9 cube minus 9 cube by 3 is 1. That means 2/3 of 9 cube is 1 into 6 is equal to 1. So 9 cube it is. So C would be 3 by 2 of 1 by 9 cube. Now if you simplify this, it should be 1 subtract 486. This is the value of C. So now we got the f of t value 1 by 486 to 81 by t square. This is the PDF, correct? This is the PDF. Second would be find out the CDF. So if t would be 0 to t. Now forget about the 9. 1 by 486 81 by t square dt. 1 by 86 to get outside. Same thing, integration 0 to t 81 dt minus 0 to t t square dt. Right? So again it will become 486 81 t 0 to t. Now it is 9 tq by 3 0 to t. So it is 81 t minus q by 3. We just multiply the number with t by 6 minus t cube by 1458. This is the FT, the cumulative frequency. You can use this particular cumulative frequency. So basically, I can write like this: t less than 0, t by 6 minus q by 1458, 0.9, and this is 1. Of course, as you told, FT has a maximum value of 1. Right? Last two problems, that is, what is the probability that gives a person waiting in the queue for more than 3 minutes? So P t greater than 3, that means P t less than equal to 3, that means f of 3, that means put the values simply in this minus p by 6 minus 3 cube by 1458. Eventually we get the probability of 14 by 7 or the 518. So almost 51% people are expected to wait more than 3 minutes. Fourth, the person who is waiting for 3 minutes also is waiting for the 7 minutes. So it is a kind of a conditional probability. If that person is waiting for more than 7 minutes, given that the person is also waiting for the 3 minutes. So this is P A by B. So P greater than 7 uh, intersection P T 3 greater than 3, and this would be P T greater than 3. Now greater than 7 minute and greater than 3 minute, of course, intersection point would be obviously greater than 7 minute itself. So P T greater than 7, P T than 3. This is 1 minus of F7. This is 1 minus of F3. F3 I've already found out, and F7 you need to find out. Just put the values there to the same process, and eventually we'll come up with the number as. So that's all. Basically, we need to take care about the discrete um, random variables, sorry, continuous random variables, and these are kind of a two type of problems we generally uh, find out in this particular part. So that's it for the continuous part. So we'll take a break now, and when we come back, we'll talk about the mean and the standard deviation of the variance for the continuous variable. So this 11:35. So we'll come back at 11:50. 11:50.